Hello guys, today we will learn about an algorithm problem in which we will change the one value into number of different coins. So given a value n, if you want to make change for n cents and you have an infinite supply of each s1, s2, sm are coins, how many ways can you make the change? The order of coin does not matter. So for example, if I have n is equal to 4 and s is equal to 1, 2, 3, so I want them change of 4 into 1, 2 and 3. So there are four possible solution. We can have 4 times 1, we can have 2 times 1 and 2, 2 times 2 and 3. Output should be 4. So we have four possible ways of getting change of 4 in the form of 1, 2, 3. For n is equal to 10, if I have a rupee, if I have a $10 and I want to break into 2, 5 and 3 and 6. So there are five solutions: 2, 2, double two three three, double two six, 2, 3, 5 and 5. So output should be 5. So let's understand how do we do that. So in this program, so we are using the dynamic programming. So in the case of dynamic programming, we break the problem into sub problems and combine the solution. So here you can see I have taken the example of 4. So I'm breaking 4 into in the form of 3, 2 and 1. So let's say if I have 4, so if I subtract 1, so it will give me the 3. If I subtract 2, it will give me the 2. If I subtract 3, it will give me the 3 1. So I have three possible ways of getting or I have three possible ways for subtracting the coin from 4. So if I subtract 1, it will give me the 3. Then again I have two possible ways. Either I can use 2, either I can use 1. Then I have two possible ways. I can go with 1 and I can go with 2. Here I can also go with 3 also. So I did not written that. So I can use 1 and I can use 2. So if I subtract 1, so it will give me the 1. Again I will subtract 1, it will be the 0 0. So I will stop when I get the 0. Here if I subtract 2, it will give me the 0. Here if I subtract 2, it will give me the 1 then 0. So if you look into that, so the left subtree, the left edge of this subtree give me the one combination. So one combination is 1 1 1 1. Another is 1 1 2 1 2 1 and 3 2 1. So these are the repeating things. So here we are using the dynamic problem. So we dynamic programming. So we are breaking the problem into sub problems for getting the optimal structure. So what I am doing, so at a time I am using the one coin and ignoring the other coin. So I am subtracting the 1 and ignoring 2 and 3. So if I using 2, then I am ignoring 3 and 1, and if I am subtracting 3, then I am ignoring 1 and 2. So at a time I can take one decision where I can use one coin and ignoring the other coin. So if you look into that, if I go to left side, then I'm using the coin 1 but ignoring the coin 2 and 3. So this is the cr- crux in this problem. So at any stage you can see I'm using one coin, either I can use 1 and I can use 2 but ignoring the other coin. So if I use this hierarchy, so here I'm using the 1 ignoring 2 and 3, again I'm using the 1 ignoring 2 and 3, again I'm using the 1 ignoring 2, again I'm using the 1 ignoring 2, and again I'm using the 1. But in this hierarchy you can see that I'm using 3 ignoring 2 and 1, then I'm using 1 ignoring 2 and 3. So this is the recurrence relation. So this is the dynamic programming solution. So there are two properties in dynamic programming. One is the optimal substructure. So in the case of optimal substructure, to count the total number of solution, we can divide all solution into two sets. So one set is solution that do not contain the mth coin, and solution that contain the at least one coin. So I'm using at least one coin and I'm also not using mth coin. So either I can use a coin or not. I cannot use a coin. Let count as mn with the function to count the number of solution. Let it can be written as the sum of count as m minus 1 n and count as mn minus sn. So what does it mean? So m is the array of coin. So count as m minus 1 n means m minus 1. So m is the array of count. So m minus 1 means I am ignoring one count. So in our case, the m is an array of 1 to 3. So if I am doing m minus 1, so it means I am ignoring one coin. I will only use the 1 and 2. Here I am ignoring the one coin, but value is as is. Next is what I can do. I will use all the coins, but reduce the one coin. So let's say it my if my value is 4, so if I subtract the 1, the remaining value is 3. So here I can use all the coins. Therefore, the problem has optimal substructure property as the problem can be solved using solutions to subproblems. So overlapping subproblems. So following is a simple recursive implementation of coin change problem. So it's an overlapping subproblems. So you can see that. So this is the recursive function. So you can see that this is the recursive function for this solving this problem. So here I am using s m minus 1, not using one coin, ignoring one coin for all values, and plus I am using all the coins but reducing the count to 1. Thanks for watching.